Okay, so let's start now. So this is the first revision session for which one, and the second revision session would be on Saturday as our usual session timing. So in this session, we'll discuss. The first thing is that there are two revision sessions for which one. So in this session, we'll try to cover which one week 1 and 2, and in the next revision session, we'll try to cover week 3 and 4. Okay. So as the week 1 and 2, week 1 is a bit new, but week 2 is totally a repetition of the.
Sir?
Yeah.
We have 5 weeks in quiz 1.
Yeah. Yes. Sorry, I just missed that. So, yes. So week also, yeah. So yeah, 1, 2, and 3. In this, the first revision we'll try to cover till week 3, and the rest 2 will be covered. 4 and 5 will be covered in the second revision. So as in the first lesson we are covering, as the week 1, week 2 is just exactly the recall. Week 1 is just new, but very basic definitions are there. Week 2 is just recall of whatever you studied in the previous, in the foundation related to maths, and week 3 is. So in week 3, topics are 4 fundamental spaces are there: orthogonal vectors, projections, and least squares. Okay. So how will we start? The best thing is I'm thinking to first I will take your doubts, whatever doubts you have, because the summary every time we are doing something. Yes, it is already on YouTube, so you can just open the channel of MLF and you can get history, or in calendar it will be updated. Then. So first, whatever you have doubt, you can. If you have doubt, please let me know.
From week 1 and 2, right?
Week 1, 2, and 3 also.
Okay, today 1, 2, and 3.
Yes. No doubt. Okay.
Sir,
Mm-hmm.
can you just give a revision of density estimation, like how to find the error and the points which we get from the function?
Density estimation. That is just a formula, Okay. So density estimation is okay, because it's just giving the just brief idea. I don't think the question would be asked on this basis. Whatever taught, So the best thing is that you can even neglect, or the formula is given for the density estimation. Let me present. I'm not presenting. Just. Okay, so density estimation is, if you have some data is given and probability map is given, so here how we'll calculate the loss related to that. If px is a large, if x is belongs to data, and low otherwise. So here all are actually just formula in the density estimation. This is just formula. If question would be asked, first of all, very less chance would be there, and if it is asked, then surely all data would be given. Like here, the probability is given, data set would be given, probability is given. I just need to calculate the loss. And the loss, how the loss? The reason is a very less chance to ask because here is the log function, and how it will be asked. So numerically, it would be difficult to ask. So this is one reason to be skip this. Otherwise, if you are concept wise, you want to know. So as usual, the data would be given, and probabilities related to that would be given. Okay. So loss means if you have a data set xi and probability mapping, it should be given already. Okay, for the particular data. Okay, means if xi is given, related to that, the probability would be given. Then how will calculate the loss related to that? So sum of all, how many data would be given, as here the formula is exactly, and then minus log of, because as you know, log lies between 0 to 1, so we want the positive value, so that's why the minus is there, and log p of xi. And if you want to see it, how we'll calculate, so exactly here, as this one is given, if xi belongs to 0 to 10, then the density is given as a px is equal to 1 by 10. That's all. So as it is given, you will just need to substitute the log values. So as here separate densities is given. This is one density. Okay, this is one. Then other density is here, and this is the next one. And then how we'll calculate the loss? You can separately calculate for each one. As this one here, it is given per data wise. We just need to calculate. Data is given here. This is one dimensional data. You can see it. This is 2.3, 2.7, 4.6, and
Sir,
sorry. Yes.
so the questions will only be on calculating error.
Yes. The question would be, yeah, that is what is only thing, right? In this here, we are only going to be the how we'll reduce the error.
It won't be like finding the probability, uniform probability function, right?
No. This you will see in 11 and 12. Because this is just a brief, how could we ask? Even we are thinking you are coming, all of your students are coming from foundation, but directly without the lecture asking from there is a bit difficult. At least it should be a recall of even all things, then asking would be easier. But here it is just for the loss is given, so you'll generally ask the loss.
Okay, so my another doubt is like in classification function, where we take Boolean values 1 into f of xi not equal to xi.
Yes.
In that, what is the value if we get 0 in the function?
If the function value is 0, okay, is this a mock problem?
Yes, sir. While doing a mock problem, I got 0 in one case, so I don't know what to substitute. I substituted 0 in that case.
No, so the Boolean thing is that if the value is matches to the function value, means the given data value, then it is 1. If not matches, then it is going to be 0, right? No, if it is matches, then it is 0, and then if it is not matches, then it is 1. This is how it is, no? If data is given, then in the classification problem, how will give the sign function is there, no? If it is no, it is sign function. Just a second. How generally we calculate loss?
Yes, sir. It's a sign function.
Sign function, no? So if suppose we have a data is given like this. Suppose here it is. Suppose This is a two-dimensional data is a kind of, let's say this is x and y, and it's a 0 and 1 minus 1, 1, maybe, yeah, 1 itself, and two classes would be generally. So, or let's say this is
function should be signum, I think.
sorry?
Function should be signum now, SIGN.
SIGN. This is the function you are saying?
Signum function.
Yes. Yes. Yes, signum function. This is the signum function. Mod of x divided by x. So it will give either 1 or minus 1. That's all. Yes.
So, but inside the sign, they will give a function, right? X square plus 2 by 5 or something like that.
So here it is, if it is such thing is there, then exactly so how it is, let me open one minute. So density estimation, classification. This is what it is. So no, this is not inside function. Its meaning is that your function value is not matching to the whatever the y values is there. That is what it is.
Yes, sir, but
So
my doubt is like inside the sign function, if we get a 0 value, so we should put plus or minus 1. What should we put in the sign if we get 0 inside?
Here, this one.
Yes, sir, if that value becomes 0, what will be f of x?
Okay.
If nothing is given, it's generally taken as 1.
No, the function will be given, but the output value I got 0. So I don't know which sign to take, minus 1 or plus 1.
Yeah, so actually that's what I'm saying. If nothing is specified as such in the question, then for 0, sign of 0, generally you take 1. Else if if you have to take sign of 0 is something, then you will have to take that basically. Like this was what was shown.
Generally, yeah, but 1 minute. 1 minute.
In the lecture, professor said that it should be taken as plus 1.
Plus 1.
Yes.
If it is 0.
Yes,
Yes.
sir.
Yes.
Then it is fine. Okay, here inside you are getting 0. Even so, yeah, in this case, generally, yeah, see, the sign of 0 is generally we know it as a 0. 0 is a neutral. But whenever you used to take the sign, so sign for 0 is generally we take plus. Whenever we are generally take, it is plus. Otherwise, we think it as a neutral. Okay.
Neutral means again I have to put 0.
No, again, no. The sign of 0 you will take plus 1. Means the sign of 0 is going to be plus 1. That's all. So if it is matches to that y values, then it is going to be 0. If it not matches to y values, then it is 1. That's how it is. Are you getting it?
Yeah, good evening, sir. Manoj this side, sir. Very humble submission, sir. If you first start, give the repetition slide, sir, that will be more convenient and we can ask the doubt later on, sir. after your revision slides, sir.
Okay.
Yes, sir.
So I have a doubt, sir.
Mm-hmm. Yes, what is the doubt?
Sir, I have a doubt regarding the column space of A and the nullity. Like,
Okay.
and there's a statement that says that column space of A is orthogonal complement to the null space of A transpose.
Yes, yes, yes.
Right, sir? Now, why not?
Mm-hmm.
It's not. Why is it not orthogonal to the null space of A? Why A transpose, sir? Could you please like shed some light on this concept?
Okay, okay, okay. Okay. So just a second. So okay, I will come to that. So while I start so discussing this, I will come to that. So that is a good question. Okay, we'll back to this. Okay, so let's do as someone said that proceed like kind of in a flow. So the first thing is that whatever I was discussing this one, is this clear that you are asked the sign of 0 is going to be what is the sign? So generally we'll take +1. And rest all, if it is a matching, as this one, the formula is there. This one, if it is matches to, then it is going to be 0. And if it is not matches, then it is 1. And by this way, we'll calculate just loss. That's all. Is it clear? No? No?
Yes,
Okay.
sir. It's clear.
Okay, so let's proceed. So, okay, so as in week 1, there are, I'll just quickly go through the week wise. So data sets, models and machine learning tasks. So data set is nothing but, as you are studying, even it's started from maths too. We think it as, data is nothing but so vector we think as a collection of row wise, whatever the arrangement is there, that is called data. Means, like this, you're vertically writing, and dimension is depend on how many. So data comes actually from, as your there is one shopkeeper, and generally he collects the data of one day. So how many peoples are, like, if it is a dal, chawal, something is there. Okay, rice, dal, rice, something is there. So you usually collect how many people bought this, in what quantity. So this collection is called data. That is what it is. This row, this portion you can call as a data. And using this data, if you want to infer something, so how he will infer? He will build a model. Maybe he hires some data scientist and want to predict that if a particular person is coming daily, and using looking his records, he want to predict that in a particular day he will come, and how much quantity of oil he will buy. That is what the prediction means. Try to predict that he wants to know in early that, or in another way that that shopkeeper wants to know that in a next day how many quantities of the groceries will be consumed. That is he wants to know. So this he will know by whatever the older data he have, using that, and he will the machine learning is, as some model it built. Model is nothing but a kind of function. No? As you have, this function is a kind of also a model. You will give something and will give the output. That is what it is. But you have this particular thing. You got this. You are building it by something in this one. But we want to make a flow to knowing that how, using these data, how you will build this particular function. How will that is called your model. That is how it is. Means how we'll know that using this these data, how we'll exactly find a function so that it will answer near about, not exact but near about at least, so that people will be aware of that, or maybe shopkeeper will be aware of that. Okay, on the next day this much groceries will be consumed by the customer, and or this much groceries will be sold out. So this is how this is the meaning of knowing the data and how the model is used there. This is the exactly thing. And to exactly getting this function, which is that model, how we will build this. So that is a big process. The process means algorithms, means whatever the data we have. So to learn that, as a computer, all of the computer is it just as the based on the history. As the based on history will give something, he can easily calculate. I mean to say how many data you will give, he can easily calculate. So it can easily calculate. So, so the mean to say some portion would be parted as training purpose. Training purpose means using the data. How we'll get this exactly model, and then training and the test data, and then final is prediction. There are three types of data: training, test, and prediction. Training data and test data. And there is any other data is right. Something name is there. Training data, test data.
Validation.
Sorry.
Validating data. Validation.
Oh, validation data. Validation data is for validating that. If it is either it could be of so many training data, validation data, and then test data is there. Three type data here. So training data is for training the model to mean to say the exactly getting, not exactly, which would be the how we'll get the model. This means train to the model. Next is validation, is how much your model is correctly giving, and test is this how means validation and test is a very similar thing is there, or even in different word. Validation is if you built it so many models, which one is going to be validate for that, or which is giving the correct accuracy, and test is finally to test that. That is what the training, validation, and test. Okay, which model is going the best accuracy or less error, then the test is just for testing. So this is how the training, test, validation, and models are there. And next is after knowing it, there are some. So knowing to be this building a model, we generally classify supervised learning and unsupervised learning. There are two classes we generally study here, at least for this course: supervised learning and unsupervised learning. So in supervised learning, there are classification, regressions are there, and unsupervised learning is dimensionality reduction and density estimation. So in supervised learning, we have classification and regression is there. So this is okay. So the first question is why the name is supervised learning and unsupervised learning. Why it is so? So the simply reason is the naming convention came as the reason is in the supervised learning. If you see the regression and classification is there. Okay, regression and classification. Some other also models are there. Some different algorithms are there. We generally hear regression and classification. And if you see it here in the regression, we have some data is given and some output is there. Means x is there and some particular y is there. Means maybe the data x side is going to be one dimensional, two dimensional, but y side is means the final, like here it is as the room price. The finally this side is room price, and this side tells you that the distances from a particular location. Okay, and this side is final price. So how many data is there? So this side is final price is there. Similarly, in the classification, some data would be given, and based on that, some classification y side also is given. So that's why here, we have some from on the top of view, we are able to see that, okay, these things are there. Means, or in the classification, we have already the classes is given. And we just need to decide that in which class this particular data, if we are giving feeding then in the model, in which class it will lie. Or here it is as this should be given, and using this means here the y values are already predicting, as we are using this in the prediction, sorry, in the build this training purpose. In doing training, we use this data to train our model. So based on this, we used to predict. So it means right side the y values is given here. That's why it is kind of supervised. Means we have some from top of view, we have something, at least this y, as here this y is there. But in supervised learning, we don't have. Means if you see the unsupervised learning, we have dimensity reduction. Okay, or the unsupervised learning is PCA is there, and another thing is there. So in this, we don't exactly predict y values. Okay, or here in the density mistration, we just predict the how much that possibility would be there, not exact thing as here it is given. I mean, in that, as in the case of dimensity reduction, we just reduce the dimension. Okay, how will, or maybe which feature is usable, which feature is not usable, or this is how it is. But there is no meaning of y. Y side is not in the unsupervised learning. You cannot see the y side, right side here, as here this one. In the same supervised, we have this y values, means exact pricing thing, or maybe classified will in which side it will lie. But in unsupervised, these things are not there. So that's why in the two classes we generally divide supervised learning and unsupervised learning. So in supervised learning, regression is there and classification is there. And if you want to see it in the formula, exactly it is given that what is a regression is there. Means we have some function, a particular data would be given. And what's that? In regression, these are the models. See that, as I wrote that function are generally called. In real life also, whatever, not real life, as you are doing in maths, functions are nothing but a kind of model. It is also you are giving some, you are feeding something x values and giving that function is giving you y values. So functions are nothing but a model. Okay. So here it is, you building a model means some function you will get that, and you will just calculate the function value, means whatever you build your model, and exact value.
No.
And how
am
much?
I audible? Excuse me, sir.
Yes.
Am I audible, sir?
Yes, you are audible.
Sir, I was saying is that this approach will take so much time to cover till week 3. What we can do here is we can solve questions and get intuitions to how to solve questions in the exam. We can cover this by previous terms sessions.
Yes. No. So I am now going to skip you. And I just started. No, week 2 is I am not going to discuss week 2 because week 2 is just recall. I will quickly jump to week 3, and week 3 is a new. So I will just slowly tell you that, no, very quickly I will tell you what are the fundamental, what is the least square. That's all I will do, and we'll jump to the questions. That's how I am thinking. I will not take week 2 because week 2 is very vast, and that is a recall, and discussing that is in this session is not even not fruitful also, because all of you are doing.
Okay, sir.
Sir,
now I am
formula sheet provided.
Yes. One day, sorry. Yes.
This formula sheet provided in exam.
Sorry, how? What you are saying?
Sir, in exam, is formula sheet provided?
No. Formula this. So here you just so here particularly you just need to remember your loss formula. That is what it's needed. Otherwise, model would be given. Okay. Data would
Okay,
be given. Data would be given, model would be given. Only just you have to remember this loss. And as you are doing as we have did least square till week 3, so this is nothing but your least square, no? This is just your least square, function value minus exact value. And this is 1 by 1, sum them all. This is your, even, this is your maths 1 formula, least square method. That is what it is, function value, exact value. And then sum them all, the differences, square them, sum them all. That is your loss. And which model, the question would be which model is the best. We just need to calculate the loss, which one is giving less loss, that is your best model. That's all it is. Easy to remember even. You are doing this all from the longer time, from the foundational level even. No, sorry, from the maths 1, first term. This is your least square method.
In this week's one last thing, what is the predictive model and the probabilistic model? What the main difference in between them?
So what is that? Predictive model and probabilistic model. So as the regression, it will give the give the prediction that, right? It will give that in the regression, it will predict that, okay, this much price would be. But in the probabilistic model, it will give the probability, okay, that this much chance or this much probability is going to be to happen that particular event. That is what the difference. Predictive and probabilistic is, the difference is, the probabilistic give the probability that this much possibility should occur or will occur if this event will happen. And the prediction is, in the regression, it is the regression model is kind of predictive model. It is actually predicting that, okay, this if this much he is going to buy, or these are the location of the house, then price is going to be this. Means he is predicting, right? Here it is prediction, and a probabilistic means it will give the probability, this much chance is there.
Yes,
is
sir.
this clear?
Yes, clear, sir. Is unsupervised learning under the probabilistic model?
Probabilistic is yeah, it is under the unsupervised learning. The density estimation is there such. Yes.
Okay.
The density estimation is a kind of probabilistic, right? That is giving the density estimation. What is that? It will give the probability, right? That is what it is. The probabilistic model will come under unsupervised learning. Okay. Clear? Okay, so let's quickly jump to this is the regression, and the classification is, we have a simple formula. Just now even discussed that in which portion it is lying. Even we have discussed just now. Somebody is asked related to the question. The sign function is there. Based on the sign, the y values is given, and accordingly, if it is the matching to that, we'll give 0. If not matching to that, we'll give 1. Sum them all. So it will give you the loss. That's how it is. So this is what it is, and then next is dimensity reduction is there. This is many people have doubt on generally that how it is. So the one example is there. If you revise your of week 1 solve with this problem, the last problem, that is exactly the dimensity reduction. Means we have given some encoder, decoder. First thing, we have some data would be given. Okay, some data would be given here, and the encoder would be given there. That is generally given in the matrix format, or maybe in the linear transformation format. Either it could be given as a linear transformation form, x plus y, or maybe if it is in the 3-dimensional and reducing to the in 2-dimensional, that is your encoder, or maybe matrix is given in 3 cross 2. So even it is very easy. We can convert this linear transformation into matrix format using the basis. All of you already doing it. Basis is 1 0 0, and on that basis you can convert in the matrix format, or maybe there is no need of converting that. We just substitute the values. So you'll just substitute the data value, it will give in the 2-dimensional data. That is what. And decoder is again back to the 2 cross 3. Again, it is going to be a matrix format, or maybe in linear transformation form. You can just need to substitute, or if it is a matrix format, you just need to multiply the data. That's how it is. I think there is one problem would be given. Okay. So we'll quickly do density estimation is just now which is given. Let's skip this. Okay. So the thing is, let me open the mock. The best thing way is the mock is there. So all of you done this mock problem?
No, sir.
All of you done this mock?
Yes.
No? So see, the first question is, this function is a classification problem. See, the y values is here, and this x is the 2-dimensional data. Many people have doubt how we will get it is a 2-dimensional on 1-dimensional. Okay, so here it is. The x is here, coordinates are there. How many coordinates are there? That's your 2-dimensional data. That is the meaning of it. So the 2-dimensional data. And this is your y side is a function value. No? So this will not generally see that. This will not say you that this is your 3-dimensional data. Okay, this is your 2-dimensional data. The input is number of inputs. No, this is 2 coordinates are there. So this is a 2-dimensional data we have, and we are based on that we just need to classify. So very quickly we can do that. I will just very so see that the function, the sign function is here given x1 minus 3x2. So here we just need to each time I am just calculating here the sign values. So here x1 minus 3y1. So here I am calculating here. So let's say I will write here the signs, and the calculation part is here x1. So x1 is, so this is your x1. Okay, this is your x1. This is your y. Just dx2. The first coordinate is your x1, the second coordinate is your x2, and just let's quickly do that. This is 1 minus 3 into 0. Okay, so this is 1. The sign of 1 is just plus 1. Sign of 1 is plus 1, right? And the second is 2 and 2. So this is 2 minus 3 into 2, and this is minus. So here the minus sign is coming, so this is minus 1. So like this we will calculate the signs. Okay, and if it is matches, see these two are matches the same for this data, so this is going to be 0. So if you calculate the loss, so for the first one will sum 0. The second one is, see these two are not matching, so this is going to be 1. Similarly, if it is matching, then you can give accordingly 0 and 1, sum them all and divide by the number of data 1, 2, 3, 4, 5, 6, 7. So 7 data you have. By this way, you will just calculate the loss. That's all. So this is your classification. Is it clear? Somebody said that somewhere I am getting 0. So after the calculation, if you are getting 0, so assume this 0 is going to be the plus. So if it is coming 0 here, so let's say this is going to be the plus 1. Sorry, this is going to be here the plus 1. And accordingly, we'll calculate the 0th and 1 and divide by the number of data. Okay. Let's do quickly the next is.
Sir?
So again, this problem is of week 1. Okay. So here it is mean square error loss obtained by fitting this function on the data set. So again, is this one-dimensional data or two-dimensional data? Anyone can answer?
Two-dimensional.
Two-dimensional. It's one-dimensional, no?
This is
Here,
one-dimensional data.
Yes.
One-dimensional, no? One-dimensional.
Will not see. This is already said that this is a regression function, and this y value I said no will not calculate as the number of, as you can see it here. This is two-dimensional data. If you including y, then it will become three-dimensional, but you will not calculate. No, y is for the output value, so that is not common data in the dimension of data. So here it is two-dimensional, as here the y is only one. This is one-dimensional. X is your one-dimensional. Means easily you can see how we are substituting the function only one value. This is not two variable function. This is single variable function. So this is how you can also get it is a one-dimensional data or two-dimensional data. As here, see this function is a two-dimensional. So that's why you can usually the input is also means here this data is two-dimensional, and see that input function we are substituting, or in the function two variables are there. This is how you can get easily also. This is one-dimensional data or two-dimensional data. Okay. So this is just a regression problem. Okay. The mean square error is there. Means whatever the okay, we done quickly the week 1. So this is the best.
Sir? I think that there is some mistake in the 14th question. I'll check that.
Okay. Okay. Just a second. Okay. Here it is. Is it?
Can you I don't exactly remember.
Are you talking about that symmetric and Argesian vectors?
Yeah.
Question number 12.
Is it 12?
For us, it is 14. For sir, I think it will be a different number.
Oh.
Okay, 12th one. Maybe.
This is the 12th one. This one, this problem.
Yeah.
So let A be a matrix, let A be a D cross T diagonalizable matrix, then which of the following statements are true? A is a symmetric matrix, necessary. Any non-symmetric matrix is also diagonalizable. We can find a basis of eigenvector for RD. Yes. We can find a basis. Because if it is a diagonalizable, means of eigenvectors will get, then it is diagonalizable, right? All of you are getting it? If we have a diagonalizable matrix, then how? So last time I was discussing, no, I was discussing that. So that if you have matrix T, then P inverse dP, this P, or maybe here I am writing P inverse generally. So this P is your eigenvectors. So if it is a n cross n, then n eigenvectors you will get, and these eigenvectors are independent. Okay, and these eigenvectors are the vectors. Okay, in Rn. So you got n vectors, which form a basis. So that is what the question is. It form a basis of eigenvector for Rd. You can find a basis of it if it is diagonalizable. So already said it is diagonalizable means this P is your making by the eigenvectors. Already this form is given. Okay, and the next is, can we find a orthonormal basis of eigenvector of RT? Yes, we can. Okay, so this is what is the missing, no?
Sir.
Yes.
It's related to unitary matrices. There was another question. It's 14th one for us.
So in
that
which
question
of the
has
following?
already been, sir, that question has already been raised. The query has been raised regarding that question in the discourse itself.
Okay.
Not this one actually.
Somebody created a post and has shared that on the discourse.
What is the problem here? Which of the?
No, not this one. So it's a different question for us.
Okay.
So in
There was
that
some,
the option is A
question
conjugate
related
transpose equals to A. That
Yeah, there are some
yeah,
options and you have to choose the correct options.
Okay, okay.
It was a comprehension type question. It had two questions as
Sorry.
subparts.
Oh, this is my portal is older.
The question.
I got the.
(13 and 14).
I got that. Yes. Okay. So in this 14th problem, the issue, what is the problem here?
So option A should also be correct, right?
Conjugate transpose. Okay, this is yes. Here, yeah, this is.
It is a Hermitian matrix. So.
This is Hermitian matrix.
So 1, 2, 3 should be correct, right?
1, 2. This is a symmetric matrix. No, this is not a symmetric, no.
Yes, sir.
But in the accepted answers, it's given it's symmetric. But when we select it, it's wrong.
It's an
in place of Hermitian.
Yes, sir, on the answer key it is wrong.
Sir, this question has been
should be A and
shared on
C.
Discord.
Yes.
Sir, I've shared the link for the discourse.
Okay.
This question has been raised on discourse. I've shared that, and the TA has also acknowledged it.
Okay, yeah, it is. Yeah, this problem is. In place of symmetric, this is
The options
Hermitian.
are wrong.
Sir,
this is what.
Hermitian matrices are also symmetric, no? If it's a
symmetric is different, no? Symmetric is when it is just do the transpose. For real number it is, for real entries, only the real matrix. We think for symmetric matrix is for only real. So if you do the symmetric means what? Yeah, if you see the one wheel symmetric, when A is equal to A transpose, but here it is not equal to it. They did conjugate also. Then it is going to means Hermitian is there. So this is Hermitian, not symmetric.
But sir, the Hermitian matrix is basically the conjugate transpose, no? So
Hermitian will be symmetric also, no, sir, in this. If
it will be symmetric, no, sir?
It will be symmetric.
Hermitian is symmetric. Hermitian matrix is symmetric. No, 1 minute. See, Hermitian, sorry, 1 minute. Symmetric, what is the symmetric definition? If A is equal to A transpose.
A transpose for real.
That's all. For real.
Yes, sir, for real.
And Hermitian is A is equal to A star.
A star.
Conjugate transpose.
Right. Yes, sir.
So here our matrix is complex matrix.
Right.
Okay.
Our matrix is complex matrix. So if we go with only the transpose thing, we just go the transpose thing, because this you are doing here, this is a different operation. So if you just do the transpose, will that is same? I don't know. I have to check it. If you just do the transpose of it, is it same? No. If you just do the transpose,
won't be same, sir.
Transpose won't be same. The conjugate is needed there. So this is just a Hermitian, but not a symmetric, no? And symmetric is for, here the option is given, but symmetric is for real matrices, not for the Hermitian. But if it is for, not for the complex matrices. If it is given, then it is not symmetric. No, symmetric definition is exactly in the definition. It is not said that you just do the conjugate of also. It is just saying that.
Sir, we can say that in so basically all the all Hermitian matrices are not symmetric matrices, right? Basically, but the vice versa is true, right?
Vice versa is true. Even symmetric matrix is Hermitian.
Yes,
symmetric matrix is Hermitian, but Hermitian matrices are not symmetric.
Yeah, in this case, correct. In this case, it will not be, probably.
If you think it, a real number could be think as a complex number, but a complex number you cannot think as a real. Okay, the same case is there. It is if your symmetric is there, the matrix is symmetric. That's fine because all entries are real. You can think at a 0 time I, each time a plus 0 time I, 0 plus I. So it doesn't matter if you do the conjugate transpose. Exactly, it is going to be the same. Means it is following this. So Hermitian is symmetric, but symmetric is Hermitian. This is.
Sir,
so here,
can we take an example regarding
this? So that is what example itself I'm taking. No, if your matrix is 1, 2, 3, if I'm doing for 1,
no,
2,
sir,
2,
for
3.
Complex, sir. For complex. Like
for
for
a complex,
1 iota,
let's
1.
say 1 I.
1 iota, iota 2.
Okay, just a second. So 1 let's say
I2.
I2.
Okay. Yes.
So if you do the symmetric here, so means a transpose of it. So here it is going to be 1, and this is I, and this is I, and this is 2.
And this is 2. And now we'll take conjugate of it.
And now if you do the do the conjugate of it, it is going to be 1
minus I minus I2.
Minus I.
But that is not equal to A.
This is not equal to A. So this is not this is symmetric.
It's not true. It is symmetric, but it's not Hermitian.
But not Hermitian.
So all symmetric matrices are not Hermitian, right?
All symmetric matrices is all symmetric matrices. So here, okay. One thing is there if you are including the real in the case of real matrices are there. Yeah, if you are including the complex, then it may not be. Yes.
But all Hermitian matrices are symmetric.
All Hermitian matrices are symmetric. That is also not true, no? As
all
this one.
Not symmetric, no?
Not symmetric. Here this one. This is Hermitian, but not symmetric.
Symmetric is Hermitian.
Here the
all symmetric are not Hermitian.
So even all symmetric matrices are not Hermitian, but the case is that all real.
All real symmetric matrices.
All real symmetric matrices are Hermitian.
Sir, but sir, generally whenever we refer to symmetric, we generally refer to real only, right, sir?
Or real only. That is what it is. If the option is given there, that should not be there. Okay. But if that option is given, then be careful with that. These are the differences exist. Only stick on the definition. So whenever you have confusion, just stick on the definition. Okay, I have symmetricity, I have given this definition. Hermitian, I have given this definition. Okay. And if it is following the problem is following the definition, then true. If not following the definition, then it is wrong. Okay, so let's quickly do this problem. So we have this data. So this is a regression problem. Here each time just need to here the x data, y data, and this is fx data. Let's say this is fx model. Then okay, so here is a 1 and the y value is 2 and the model value is going to be 1. Each time just need to evaluate here. So 1 minus 2 upon 5. So whatever the value will get, let's calculate here. Similarly for 3, 4 and the value calculate here like this. We'll just calculate. Okay. Now Here it is the mean square error is the given. That means sum of mean means 1 by n, and square error means, okay, we calculated here the value 1 minus 2 by 5. This is minus 1 by 5. So the 1 minus 1 by 5 minus 2 is square. The first one. For this one also, okay, this is a function value and this is y value. So again we will write like this, the brackets, sum them and divide that. That's how we will calculate the mean square error, or this is the regression problem. Mean square error, sum square error, least square error, almost all of are the same. So this is how we'll calculate the. Next problem is on the week 1. Okay, density estimation. So see again, if somebody is asked the density estimation, see that for this is also one-dimensional data, okay, as here only one-dimensional data, and the probability of each one is given. That if it is lying between 0 to 5, then it is going to be 1 by 5, and if it is outside of 0 to 5, the probability is 0. So just need to calculate the likelihood loss, or means likelihood loss means just loss of the model. 1 by of minus, okay, so 1 by number of data, how many data we have. So okay, if we calculate here quickly, we can calculate even the density estimation. Everything is given. So whenever some problem is given, the model is already given. Means here the probability model or a probabilistic model. So in this problem, the problem is given for the density estimation algorithm, and this is one-dimensional data. Okay, as the x1 is there, the real values are there. Okay, and now we just need to calculate the likelihood loss. It's loss. So how the formula is given? 1 by number of data minus log of the p of x. I is if you want to mention. I. So each time let's calculate phi of xi first of all. Phi of xi is going to be, so here is, so the x1, sorry, xi or x values p of x. Okay, so here it is 2.5. So yeah, it is lying 2.5 lying between 0 to 5. So here is 1 by 5. Okay, 1 is there, this is 1, so again 1 by 5. Okay, fine. And then 3 is there, so it is again 1 by 5. 4.5 is there. Okay, all are actually values within the 0 to 5. 1 by 5, 4.95 also within that. So 4.95 is also 1 by 5. Now, how the loss is 1 by n summation log of 1 by 5. Each time you just need to calculate minus of. So for each time xi p of xi. So again minus of log of 1 by 5 minus of 5 times. So it is going to be 1 by n minus sum of it is. So minus log of 1 by 5. Here is 5 times. So here it is going to be, so here number of data is 5. So 1 by 5 summation. So this is what is it? So sorry, I am just missing, not 5 times. So how it is? This is 5 by 5, right? Am I wrong? This is 5 by 5 minus of. So this is 0. So finally it is 0, is it?
How it is?
No. I just missed that.
It is 5 times, no?
5, sorry. I thought maybe it is 7 multiplied. Sorry, this is 5 times 1 by 5. And so log value would be given there. I use the log base 10. So just need to you have to use the calculator. That's why the density estimation you'll use to calculate. Okay. Any other problem on week 1? No.
So sir,
okay, this is
in this
encoder
question,
decoder. Yes.
Excuse me, sir. So sir, in this question that we just recently solved, so the p of x, this is like the loss that we are calculating? Like for every loss, we are getting it.
No, this is the
We're
probability,
calculating
no?
the
P
value.
of x. This side is
It's a probability.
not loss. This is the value we are calculating, the probability.
Okay, so this is
Density
desirable,
function
right?
will give the, huh?
Is this desirable or is 0 desirable? For a density estimation model. In this example, is 1 by 5 desirable or is 0 desirable?
So 0, no, 1 by 5 is right. Desirable in the sense of how we are saying it.
For best fit, or for the like, this is the right match, or the loss is the minimum, for which loss is minimum.
No, see, in the density estimation, the density function is given this one as this is how it is. In the other, this is a probabilistic model. So see, you are not calculating here the probability. You are not calculating the probability here. It's already given that for this particular data, the probability is going to be this for this estimation. The probability estimation is going to be this one, how it is. For the different model, maybe some 1 by 4 would be given. So for each time, if you want to calculate for other one, let's say this is P1 and this is P2. So this would be given differently. We can calculate that. And which one is giving the loss? That is this is a probabilistic model. And it is given as in the form of density estimation.
Okay, so sir, for this one,
sorry,
like
in the case of density. Yes.
Right. So sir, for all the probabilities to be 1 by 5, so the right side of the calculation, this is the loss that we've calculated, right? 1 by 5
this is
minus
the
1
loss.
by log. This
Yes,
is the loss.
this is the loss.
And so is it like, and if we had all the zeros, then
if it is all the zeros, then your model is actually, in the sense of it is a good model. That is what it is. All zero means you are not getting any error. It exactly giving the as your value is there. Means here you don't. So what is the meaning of that? Like if you are getting 0 or whatever you are getting.
log of 0.
Log of
0 will be
infinite, right?
infinite.
So that would be like the worst model, I guess.
Yeah, that is what in the lectures professor is said. No, if you are getting infinity, then how? That is what in the lecture already there.
Okay, got it. Yes, sir. The probability must be 1. The best fit is 1. Got it.
Oh, so this encoder decoder is given here. See that how I said no, it could be given as the linear transformation form, or it is given the kind of this is also in the this is linear transformation. This is also linear transformation. GU used are used to reduce the dimension of the data given below. What is the loss obtained for this model? How we'll calculate here? Easily we can calculate.
So while I was doing this question, it took me a long time for all the 4.
Okay.
So I don't know, like in exams, if they ask this question, how much time will go in the single?
No, why it is taking long? So let's do quickly that how it would be. So this is f of x. So this is okay. You'll get one dimensional. Okay, this is one dimensional. So the case is that this data is given. You will feed in encoder. Okay, and whatever the output you will get. Okay, you will feed that in decoder. And finally, you'll get the 3-dimensional data. So means here, first of all, it is in 3-dimensional. when you put, see that you are getting a one dimensional. In reducing to the one dimension, you are getting a real number. And after getting a real number, you'll give into the decoder GU. See, this is GU, each time is, and this is giving you in the 3 dimension, 3 coordinates are there. This is how it is. So let's do one by one. Quickly, we'll do one by one. So for this one, f of x is going to be what? Here is this is your x1, this is your x2, and this is your x3. So -1 -1 plus 0.5. This is -1. So this is going to be -2, and this is minus 0.5. So this is finally -2.5. Now apply this on decoder GU. So GU is this is your U now. Whatever you got, this is your U. Now apply on decoder. So this is going to be G of decoder is 0.3 into -2.5 minus
0.415.
And sorry, and this is -2.5. So finally the vector you'll get here, this is going to be -7.5, 2.5, -2.5. This is the first one. Similarly, each time we'll calculate this one. Okay. Okay.
It should be 0.75, no?
Oh, sorry. 0.7. So you got this one. Okay. Now this is how for the second one you just need to calculate similarly. Okay. For each time you just calculate. Now it's saying calculate the loss. So here these values are your original values, and after encoding decoding you are getting these values. So how you will calculate the loss? You'll calculate one by one. Like this is your for this is -1, 1, and -1. And now from original one, or maybe whatever from original one you are obtained one you can subtract, or from obtained one you can subtract the original one. It doesn't matter, because at the end we are finding the norm. So this is 2 minus 2.5. Just need to subtract and find the norm of it. So here is for each time we'll calculate the norm here. For the first one I calculated the norm. Similarly, you just need to calculate the second one and calculate the norm of it. And similarly for each one, you calculate the norm and sum them all, divide by the number of data 1, 2, 3, 4, 5. The first one, how we'll calculate the norm here? We'll just need to. This is a minus. Minus here it is minus 0.75. So this is minus 1.75. 1 minus 2.5. So this is 1.
Sir, it will be 0.
Yes.
The first one will be 0.25. The first one will be 0.25.
No, here this is minus. Okay, this is plus. Okay. So this is 0.5. So 0.25. This is minus 1.5, and this is minus plus again. So this is again 0.5. And now the norm of this one is going to be norm square. So norm of this one is going to be, or norm square of this one is going to be 0. Yeah, it is a bit calculative. So minus 1.5 square plus 0.5 square. This is the first one, norm square. Similarly, each time you will calculate the norm square of each. So square is square is square. You will get the positive value finally. Okay? Between so whatever the loss. This is how you calculate the loss.
Sir, is this analogous to mean square error?
This is a kind of mean square. Yeah, this is kind of mean square error. Actually, from the exact value you are subtracting after encoding decoding. One means whatever the model you are after applying that exact value and the obtained value, and subtracting them, square them. This is a kind of mean square. You are taking the mean. Yeah, one thing is there in the mean square, you just calculate, your mean values are actually real number. But here you are first finding the norm. You are making the mean value, sorry, real number, norm. You are finding the norm and then sum them and divide by the number of data. This is how it is. Kind of a different, but the same meaning is there. Okay. So this is how it is. So week 1 is almost done. Almost concept we have discussed. Week 2 is I'm exactly skip because these are the set function, calculus, linear approximation. You have to just recall that. I will go through with the questions. The best thing is I will go through the questions. Let's move on to the week 3. This is one.
Sir, excuse me, sir. I have a query, sir.
Yes.
So regarding this recent question that we solved, sir, why is loss taken as this mean square? Why not root mean square?
Root mean square. Okay.
Because in statistics, it's related to statistics, no, sir?
No, this is not for the statistics. The first
mean square and root mean square, they are actually calculated in statistics, no, sir?
Root mean square. So yes, the first thing is then the one is the reason is the first is the root is generally the root is we have plus or minus both. The sign are the root of generally plus and minus both. But here is that is why we are in place of root we are first squaring them. So means we are squaring them. Means we want the positive, not the negative. That is why we are squaring them each time.
Right, sir. But the root will be taken after the addition of squares, no, sir? The result of this sum and the average is
that could be
root.
even in that case, yeah, that could be done. Yeah, that could be. So it's depend on how we are calculating the lot. We generally use this formula. It's depend on you, or it's depend on how it is taught. So here we are calculating for mean square. So means this kind of error. You can calculate or how the formula is given. We can proceed with that. Totally right. In statistics, the root square error is there. You can follow that. That is there. Here it is a mean square. Exactly fine. No issues.
Sir, I just recalled because it's used in calculating either the standard deviation or the variance. That's from there I could connect. Because there
so it could be calculated. It could be calculated. There is no harm even to calculate. It's depend on that, how we are calculating. So actually the reason is see, you want to make it complicated, so you can like here you are saying sum them and then they find the root and then find the mean. So that could be done, but here we just want to compare. Here what is happening? We want to compare only. So if you have two models, suppose you have F1 and you have F2. So and you got the root of it. Root mean is something, and here is root mean is something. So you calculated a lot. You calculated the root also. But if you do the one previous step, before doing the root, if you just compare this, that is also you are able to compare which one is the best, right? So no need to do the root of it. One step ahead itself telling you which one is the best.
Right, sir.
That is one also reason we are not moving to the root.
Got it. So basically it's the variance, sir, right?
Yeah, it is a variance, right?
Right, this is the variance. Huh?
Yeah, this is what the variance kind of means exact value. Yeah,
all loss functions we are seeing, these are all just the calculations of variance from data sets and the real and original value. And
yes.
Okay.
Yes. Yes, exactly. Okay, the second week I will try to cover with the questions. Let's move to the third week. We will quickly cover this week 3. So in week 3, the 4 fundamental spaces is there. And the 4 fundamental spaces are space column space,
Null space,
and left null space. All are easy to calculate. All are exactly easy. Row spaces, just take the rows. If you have a matrix, nothing is there. Just take the rows, take the span of it. That is your row space. Column spaces, you have columns. Take the span of the columns. That is your columns. And null spaces are different. And this one you are doing from very starting of maths 2. Just need to calculate is which one making or which what is the vector exact. If you are multiply that, you are getting the 0. That is your null vector and null space will form. So how many vectors you will calculate means you will calculate with the 0 will lie in that. So that's why it is called the space also there. It will form a space. The null spaces means how you are usually calculate the null space. The left null spaces take the transpose of matrix and then calculate the null space. This is your left null space. And somebody's asked that column space and null space of A transpose, right? Means these two, left null space is orthogonal. Is it? Is there? I don't know is there or not. So he asked that why it is so the column space is orthogonal to left null space. And this row space is orthogonal to the null space. I think this is what it is.
Sir, he had asked why we only say A transpose instead of A null space of A.
Why we talk about the this A null space of A transpose?
Yes, sir. He asked A transpose.
Sorry. Why we are finding the null of A transpose? Is this the question?
I don't know the question, but it was something about A transpose which he asked. I'm not the one who asked the question.
I got that. So he is talking about how the orthogonality is that. How it's happening means this column space is orthogonal to the left null space. The problem is actually I got that column space is orthogonal to the left null space. The simply reason is even from here we can get the column space is span of the columns. If it is we are doing in 3D, this is 3 cross 3. So the column space is the span of the columns. And if you see the left null space, if we are doing the transpose and then we are finding the null of it. So these columns become rows. We do the transpose of it. The columns become rows. The column is changed. Now, if you are finding the left null space, which is just finding the left null space, is finding the null space of A transpose, which is now this one. Now, if you see x, y, z, you are multiplying this to this matrix. So you will form an equation. Like this will form an equation. And you are finding the x, y values which give the 0. What is happening? You are kind of doing the dot product. The values you are finding a kind of dot product you are doing. So these and this vector is, you are making the dot product, you are getting the 0 vector. This is what it is. When you are doing dot product, you are getting the 0. So that's why the column space is, this is how the connection is. The column is orthogonal to the left null space. This is how it is. The simple relation. Easily we can get it by this relation. Also by this picture even. Okay. So the 4 fundamental is nothing but row space, column space, null space, and left null space. Okay.
So
the next, yes.
Is row space of A is the parallel to the column space of A transpose?
Row space is parallel to the column space of A transpose.
Yes, yes. Means what happen when we do the transpose of an space?
So row space is yeah, that is not parallel even, exactly the same space you will get. Parallel is there is no meaning the space word, means same space you will get, because you are saying the row space. Okay, that is, suppose you have matrix this, you are talking about the row space. So this is your row space, you got the row space. Now we are saying that you are finding the transpose of it. So the rows become now column. Now if you do the transpose, your rows become columns. I am saying that the column space of this one exactly the same. You are finding the span of the row space is finding the space of these vectors, and column space is finding the span of exactly the same vector it is. So both are actually same, right? The column space is the same. Sorry, row space is the nothing but the column space of A transpose. The same things there. You are getting the span of the same vectors. There's no change here.
Here bases are different in
basis for a one space. There are so many bases, infinitely many bases.
So the standard bases are same, right?
A standard order basis.
They're same, right? Which is transposed.
Transpose. We are doing the transpose. That is same.
Sir, actually, there was some network issue regarding with me. So could you please repeat the part? I had asked the question in the beginning that why the null space, or sorry, the column space of A is orthogonal to the null space of A transpose.
Left.
Could you please?
No, not null. Left null space.
Sir, null space of A transpose. No?
Null space of A transpose. Null space of A transpose is nothing but the left null space.
Left null space of A.
So null space of A transpose is nothing but your left null space.
Right.
So how it is happening?
Yes, sir. Please go ahead. That's what I was.
Okay, so let me repeat it again. The column space is orthogonal to, you are saying, the null space of A transpose, which is nothing but left null space.
Right.
If you see the definition, left null space is nothing but the null space of A transpose. This is the definition. And why it is so? The simple reason is, suppose I have this matrix. These are the columns I have. Suppose it is a 3x3 matrix. Okay. So this is the column. So column space is going to be a span of these vectors. Span of these vectors. Now, okay, fine. This is your column space. Now you are saying that let's find the null space of A transpose. So do the transpose, the same column become rows now. Same columns become rows now. If you do the transpose here, the same columns become rows too.
Right.
Now you are finding the null of it. So we are finding the null of it, null space. So how you will find? You will just do multiply x by z and equate it to 0. So what you are doing here? You are just doing, you are taking this vector and doing the dot product with these row vectors, right? This is what is happening. This is what is happening. If you multiply this, you will multiply to this vector. What you are doing? You are just doing the dot product between these two. Dot product with this vector to this vector.
No, sir. The dot product with the column space, sir. Not with this. Transpose with the column, sir. We are doing the dot product with the column.
How you are multiplying? No. Sorry. Suppose this is 1, 2, 3, 4, 5,
sir,
6.
X. Yes, sir. Like x dot y. That is dot is the y product. So it's x transpose y, na?
Sorry.
Sir, when x dot y is the product, like dot product x dot y, so by definition it's x transpose y, na, right, sir?
So yeah. So what is happening? So the vector is going to be, the row vector is going to be 1, 2, 3, right? And what is happening? If you multiply, let's solve this. How you are solving? So if you solve this, means if you are writing in the system of linear equation form, this is going to be x plus 2y plus 3z, right? This is what it is. 4x plus 5z plus 5y plus 6z is equal to 0. And this is 7x plus 8y plus 9z is equal to 0. And here is, think this is your row vector. So vector is generally we write this one. And what if you do the dot product with the same x, y, z? So that means how you will do the dot product? This vertical become
transpose
transpose v, right? This is how it is.
V.
If you this is uv. So that means here 1, 2, 3, and this is x, y, z. And if you do the now the dot, so same thing you are getting x plus 2y plus 3z. This is what it is.
But in the second formula that we are on 1, 2, 3 transpose, here we are doing multiplication. The dot product is with the real vector u, na? The dot product is with 1, 2, 3 column. But when I transpose it, it becomes some simple multiplication. So I can't say that 1, 2, 3 dot.
No, so this is what it dot is happening.
So this is happening. This is multiplication, and the last part that we find the value
this
for,
is
right?
So yeah, this is multiplication is happening, fine.
But u dot v is not equal to when we say,
now,
we say u dot v, sir.
Now, so this is your transpose one, no? This is your transpose matrix. What is the original matrix? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is your original matrix.
Right.
This is your original matrix. I took the transpose directly here.
Right.
This is your original matrix. Now take the span of it. What is happening? Just a span of 1, 2, 3, 4, 5, 6, 7, 8, 9. This is your column space.
Right.
And now what is here the solution? Whatever you get the solution, this is the kind of the same vector here. These vectors you are just taking the dot of it, and this is how you are getting each time. So if you solve this, you will exactly get the null space. If you solve this, you will get the null space, which is nothing but the left null space or the null space of a transpose. So this vectors are what you are solving here. This, if you are multiplying these vectors separately, see, you are finding the null of it is nothing but you are taking the dot of each time with these vectors. That's why the column is going to be okay. Just see it. Just see it. This is what is happening here. Try to think yourself. This is what it's happening. In backend, it is happening.
So, sir, can I say that the column space of A and the null space of A, they are either parallel or lie in the same plane?
No, column space and null of A is two different. Column space and null space of A transpose means left null space. Only these two are orthogonal.
These are not orthogonal for the parallelity or for same or similar.
So
can I say that
means spaces are not going to be parallel. Vectors are generally going to be parallel.
Yes, sir, but they can span to space or a plane, right, sir?
They can span the space or plane.
So, for example, column space of A and null space of A. So, are they like in the same sort of plane or same sort of this parallelism? Is some parallelism is between them, or some are they similar sort of thing? Because in that part,
I'm not sure about this infer that they are parallel, but this is the sure thing is that column space is orthogonal to the left null space. This is the sure thing from here itself, and the theorems are there. We can say I am proving with the example. The proper proof is there also with the proper inner product sign. So that could be proved, and I think professor is also proving it with the V transpose kind of U transpose of V way, and seeing this different way of inner product. So, but I'm not sure about the null space and the column space. Means null space of A and the column is of A are parallel. I have to check it. I'm not sure about this.
Yes, I was curious about this because then, if they would have been orthogonal, so we would have said, okay, you know, they are like orthogonal, but null space of A transpose is being
surely it is
orthogonal.
not parallel. One thing is that surely I am sure that it is not parallel. The column space of A and null space of A are not parallel. The simply reason is then you are saying the null space of A and left null space of A are orthogonal, because column is orthogonal to left null space, right? So in the different meaning, you are saying the null space and the left null space are orthogonal to each other. This is not true. This is one thing is true. The column is orthogonal to left null, means null space of A transpose. This is true. This is a theorem, and this is here. It's look like also. I don't know you got or not, but it is actually, this is what it's happening. The dot product is nothing but this is what you are doing, and this is how we are getting. So column is orthogonal to left null space, but column and null are parallel. This is not true. In general, it is not.
Right. So, sir, does transpose bring some orthogonality to any vector space or matrix? Like we transpose this matrix, na, C or A transpose, and then we calculated the null, which is multiplied by XYZ. So can I say that, or can I think in this way, that transposition of a matrix brings some orthogonality factor?
Yeah, orthogonality. The reason is, yeah, that is what is happening. The inner product is nothing but of between two vectors is kind of transpose we are doing. So in that way, okay, if you are thinking that way, that is true. That is true.
Right, because norm is also there, no? Like A transpose A is the square of norm.
That is, yes. Yeah, in that case, you are thinking, yeah, that is true. That is true. Yes.
Okay, so if I transpose it, and then it becomes a multiply vector, and then becomes null of it. Null of the other.
Just think it. It is actually exactly looking. You can even guess. If you try yourself, you can exactly match it. The same vector is the same vector we are writing in the row wise, and if you are multiplying, this is nothing but the dot is happening, and that's why we are solving it, and that's why it is the orthogonality happening. This is a simple reason.
Right, sir. And sir, relating to this this concept, there is one more doubt I have. Like, sir, for column spaces, when we try to find the rank or span, so we do row operations, right, sir?
Row operations.
Okay, so if it's transpose, like if I go for the row space of A, so will I also there be doing the row operations or column operations?
See, the reason is, whenever you are doing, so see, there are two type operations: row operations and column operations. So
right.
If you are performing row operations, so only perform row operations. Okay. If you are performing row operation, so always perform row operation. Don't mix with the column operation. If you are performing column operation, so perform only the column operations, not the row operations. Don't mix with the row operations. This is the one distinguished thing we want. Means these things are happening. These things are needed. So if you are performing only row operation, so perform only row operation. Don't perform column operation in that also. Okay, so don't mix with these two. If you are mixed these two, then there is one thing between the why only we are sticking on this perform only the row operation, means doing the row operation between the rows doesn't change much, means in the sense of because you know the spanning of the vector is not changing the direction. So here, if you are doing the row operation, you are not maintaining you are not changing the direction. You are maintaining the direction and doing the operations. That's why only perform row operation, and or you are performing the column operation. So maintain the directions between the columns. Don't perform the row operation in that. Okay, that's why we only perform the column operations, perform only column operations. The reason is we don't change the direction. The rows actually represent a vector. These rows represent a vector. So we don't want to change the direction. We want to maintain the direction. And if you do the row operation, no, it will not change the direction of the row vectors. Similarly, it will not change the direction of column vectors. So that's why stick with the only row operation or stick with the only column operation. These two things are there. I hope it is makes clear.
Yes, sir. Regarding this, I was saying that if I have a matrix A, for example, that has column vectors. Okay, so there in the examples in the questions that are shared in the videos, so there the tutor is performing the row operations, sir, to calculate echelon form and all others form. So they are performing row operations. My query is like if I transpose that, like A transpose I do, so there also should I perform the row operation or should I perform the column operation?
Only row operation. Only row operation.
There also, like in the transpose also, I should perform the row operation.
Only row operation.
In the transform also, right, sir?
Transform also, because so see here in this course only the row operation taught. So that's why you are doing the transpose and performing the row operation. Okay, in the rough, as we did in a MSc or BSc, there we studied row operation and column operations also both. So we don't do the transpose of it. We directly do operations on the columns only. If somebody says do the transpose and do the row operation, we don't do. We directly do the column operations, because doing the column operation on the columns and doing the array and transpose it and doing the row operation, both are same. Both are same. So that's why. But you in this course only taught row operation. So that's why transpose it and do the row operation. Okay.
Right, sir. But
Don't mix or don't be confused.
Yes, sir. Yes, sir. I will only stick with one, sir. But sir, in regarding this, just one follow-up question. Like for this column operation, if I do row transform, and if I on the A transpose, if I also do row operation, will it not change the basis vectors of both these? Like basis vector must be same, na, sir. Either it's transpose or
Must
the
be same. Yeah. No. If you are, yeah.
Sir,
It is going to be the
for
same.
example,
It is going to be the same. Correct.
For example, could you please take an example, simple real matrix example?
Okay.
2 by 2. Okay, sir. 3 by 3.
Okay.
So
Okay.
if
1, 2, 3, 4.
Yes,
okay.
Sir. So like this is A and this is column vector. So if I do some echelon form, row echelon form, so this will be this times this.
This is easily. This is 1, 2, and this is going to be 0, and this is 3 times 6. This is minus 2.
Okay,
and echelon form is going to be 1, 2, 0, and 1. This is echelon.
Yes, sir. Right, sir. So the basis vector will be 1, 0, and or I think we should add this one also, sir. Like minus 2 and 2, R1 plus R2, so that the upper second element of upper row becomes 0 also.
So here the clear thing is that if you want to find the column, okay, column basis for the column space. So this is your column and this is your column. So this is your basis for the column space.
Sir,
basis for the column space.
Yes, sir. If I go for standardized, sir, can I subtract add row 1 and row 2, right?
Even you want to find the basis, even you can change this to a reduced row echelon form, and this is going to be 1, 0, and 0, 1.
Right, sir. 1, 0, 0, 1. Now, if I transpose this one, a matrix A.
Okay, let's transpose this. This is 1, 2, 3, 4. Okay.
Yes, sir. Yes. And now, should I, if I do a row operation, so I just want
let's
to know
do the
that
row operation. This is 1, 3, and this is 0, and this is 2 times 6, and again minus 2. And finally, this is 1, 3, and this is 0, 1. Okay. This is what the row echelon form.
But the bases have standard basis.
So, what is a standard basis of what? Row space, column space for what?
So they should have been only transposed, not changed, right? Standard basis. Even if I do transpose, the span of A should be the only transpose,
No,
like it
so
should not be.
you are making the confusion. So the steps, let me tell you that. See, the
If I
basis, the way it is that, let's say, let me clear that. If you have a matrix, you want to find the row space of it. So perform the some row operations, find the simple basis. So perform the row operation, take the simple rows, and that is your that is your basis for the row operation.
basis.
Now we
Yes.
want to find the column space. Okay, suppose I want to find the column space. So what you will do, we'll first transpose it. We first transpose it. So the columns become rows now. The columns become, previously it was it was columns. Previously here, I want to find the column space of this matrix. So these are the columns. But when I transpose it, the columns become rows now. Now perform some row operations. If you perform these row operations, so some rows, let's say one last row is skipped, means all are 0. So only 2 rows you find. So this simplified. So take these 2 rows. This is your basis for the column space. These 2 rows are the basis for the column space. Why the reason is simply because we just converted. You converted this column as a row wise and nothing but. So these rows are actually the basis for the column because you are nothing changed. We did transpose for doing the row operations. We changed this to do the row operations to get the simplified rows. Sorry, to simplified columns. I think it is clear now. If you are getting still confusion. Is it
But
clear?
this raises another question. Yes, this I got it. But regarding this, there is just one question. Like for the A transpose, if I see for this operation, so it becomes an non-invertible, a singular matrix, right, sir? But A is a singular matrix. Is it possible that A is
No,
non-singular and A transpose is non-singular?
No, never. If A is a singular matrix, so if you are doing the transpose of it, surely that is still singular and last row becomes 0. If you are changing proper
If
in
A
the
is, if A is non-singular, so A transpose must be non-singular also.
yes, because there is if A is non-singular, the A transpose is also non-singular. If A is singular, then A transpose is also singular.
Singular.
Okay, I hope we discuss a lot on this. Let's move to now.
Yes.
One is
Thank you,
concept is not. I didn't clear out doubts. Is it clear to? Is it clear all doubts? No, still doubts are there. Okay, so these are the 4 fundamental spaces. Then orthogonal vectors are there. About the projection and least square is just a second. Okay. Okay, so projections. The better is going with the problem because discussing the concept is enough now. Let's do some projection problems. That would be more simple. Oh, so many. There's no problem on projection. Yeah, okay, this problem. Using the least square approximation, find the length of projection vector P onto the column space of A. A, where is that A? This. Oh. So this is the least square method. So we have this system of linear equation. Okay, so as the answer is there, this is inconsistent. Okay. This is not consistent or inconsistent. Okay, this system of linear equation is inconsistent. Means there is no solution for this. So this is what it is. There is no solution of this. In this case, what we will do, using the least, the next problem is based on that. Using the least square approximation, find the length of projection vector P or a projection vector P of B onto the column space A. What it means that, see, the least square approximation is nothing but, the least square projection is nothing but, sorry, least square approximation is nothing but your projection of this B on your column space of it. Least square approximation is nothing but projection of B on the column space of A. That's all. How I will get this least square projection? How will get this projection? So simple formula. I will go with just only formula. We have A is given. So what we will do? We will find the A transpose A, and now we'll solve this system of linear equation A transpose B. Whatever the solution of x, y, z you will get, that is your projection. That is your projection of B on the column space of. That's all. So the question is, find the projection of B. So you will find the value of x, y, and z. You'll find the value of x, y, and z. That is your vector. And find the length of, means find the norm of it. In answer, you will just need to put the length of this, means a norm of this vector. Means whatever the solution you want, this have the unique solution. That is what the problem is.
Okay, sir. I can do it. No need to further discussion. Thank you, sir.
Sorry?
No need to further discussion. I can do it. Thank you, sir.
Yes.
Excuse me, sir.
Yes.
So regarding this, I have a query. In the lectures, they are given two formulas. The first one is the matrix one, and the second one is similar, but there are two formulas. Like the first one is A into A transpose A inverse and into A transpose. That is the projection of A.
Sorry. Sorry, what is that?
A into
A
bracket,
into
please open parenthesis.
Okay.
No, sir. After A.
Okay.
After A, there's an open parenthesis.
What
and
is that?
then
You
there
just
is projection. That is regarding the projection formula. So A into bracket A transpose A, and then bracket close and inverse.
This
A,
is
sir.
what?
Only A, sir. Only A, sir. No B. Only A.
Sorry, could you repeat please once again? A.
A.
Okay.
A bracket A transpose.
A transpose.
A.
Oh, A.
Is within bracket. Within bracket. Yes, sir. Correct. Within bracket, and after the bracket A transpose.
After the bracket again A transpose. Okay.
And above the bracket part there is inverse of, like ATA inverse. No, not one, sir. The middle part, the middle bracket, no, that we have used. This middle, yes, sir. This is the projection of it. And the other formula they have also mentioned is A transpose upon A transpose A for the projection.
That is your A. That is your
A transpose.
A transpose.
A transpose upon A transpose A.
A transpose, A transpose upon A transpose A.
Yes, sir. This is also there given the
A
projection.
transpose A upon A transpose. This is the formula.
No, sir. A transpose A transpose upon A transpose A.
A transpose upon A transpose
Yes,
A.
sir. This is the form.
Okay,
Yes,
okay. This is your projection matrix, sir. Yeah, this is.
Yes, sir.
This
Because
is a projection.
the A transpose A is a scalar now. Scalar can't be in the numerator.
This is a scalar. Sorry, guys.
Yes, sir.
So this is your projection matrix, and this is the formula. I don't know where is this the formula. Is
Sir,
this
this is
formula
also mentioned. Yes, sir. It's mentioned in the lecture, sir. So I just wanted to know which one to use in under what conditions, which formula should be preferred.
Okay, let me check.
Yes.
Let me check this formula. Where is that formula? Have you remembered that formula somewhere?
Sir, I had seen it, but I have.
There is not such formula.
So this formula is there when we are directly using it to find the projection, basically.
The second one.
A into A.
Second one.
Not this one. Not this one. Not the one which you showed. One which he told us, sir, projection matrix. That is basically used like, you know, when basically two vectors are given.
This is the direct one to find them. Where is this formula I am searching? This is the projection. Where it is this formula for the projection? This is it somewhere? Anyone can tell? I don't think this formula.
In the lecture, sir, it's mentioned in the lecture.
Maybe sir, while derivation, they might have used that.
In derivation,
yes.
They have used capital A, the capital A part, capital A.
This is capital A. Is this capital A?
The above one, yes. All are capitals, sir. Capital A.
Sir, there are two formulas, sir. One is projection on line and one is projection on space.
Space, okay.
This is projection on space. You boxed it, right?
Okay.
Here
So
is
this is
projection on line. The round circle you mentioned, A transpose by A transpose.
This is a projection on line.
This is projection on line.
Correct. This is projection on line. And this is a projection on column space. Okay. So you are mentioning, so that's why I a bit confused here is writing an estimate. This is a projection of see, this is derivated from here only, no? See, I wrote this one. So this is what? This is a kind of projection, no? So if you do it here, this is going to be what? If you find the inverse of it, this is going to be x, y, z is equal to A transpose A inverse of A transpose.
And B, sir.
So B is the this is the project. So you are right. Why you are saying here is A? This is not A would be there.
A,
I
sir.
don't think
it is A. It is A, sir.
It is A. 1 minute.
Huh.
Am I writing the wrong form? Let me 1 minute. Let me check just a second.
In this formula, sir, if you open the inverse now, so it turns out to be identity. Sir, I think it will be in lecture 3.4. These squares and projections onto a subspace.
3.4, relationship and projection.
Must be there. I have read it. I don't remember where it is, but it's there.
Yeah, I think this is correct. Okay. This is what it is. Okay, so here it is. Okay, so here on the projection P is equal to A.
Yes, sir.
And this is A transpose inverse A B.
Yes, sir. Yes. So my query is under which condition should I use this form?
So this is this is for when you are okay.
Sir, in this case, basically, this is for a line, right? Basically. So in this case, anyways, A transpose A will be a scalar. So it will automatically go down. So in the top, we'll have A into A transpose. And in the bottom, we'll have A transpose into A.
Sorry. Could you repeat, please?
Yeah. So basically, sir, can you just go back to the slide? Yeah. Yeah.
Yeah.
So basically, since in this one, basically, can you just show that formula once, sir? A into A transpose.
Oh, okay. This is here. It is okay. This formula, no?
So basically, what, because since this is for the line thing, so basically what happens in this case, anyways, A transpose into A is a scalar. So basically, this will automatically go down. So at the top, we'll have A transpose divided by A transpose into A, which becomes a projection matrix into B. Basically. So from there only we get the derivation, basically. The final projection matrix of B vector, basically.
Yes.
Because A transpose into A is a scalar, right? So it can easily go down.
A transpose A is
scalar, so it's a dot product, no?
It is a dot product, but here it is a vector. A is actually matrix, no? Is this a matrix?
Sir, it's a space, sir. So that is why it comes as matrix. If it is a line, it won't come like this. So it will go down, like he said.
If it is a line, if it is a line, means if it is a vector. If it is a single vector, then this is good.
A transpose by A transpose A. So if it is a space, it will come up as an inverse because it's a matrix.
Yes.
But what difference does it make? Like this will also produce a scalar. Scalar can go down, right?
No, it's a matrix, right? A transpose A is a matrix, right?
But ma'am,
it's not a single vector.
But matrix will be a 1 cross 1 matrix, no?
That is your scalar generally. 1 cross 1 matrix is generally scalar, no?
Scalar.
Yeah, so it will go down.
So that is good.
If you are writing 1 cross 1 matrix, is an inverse of it is just 1 by F. That's why it is good. It will go down. Okay, so this the other which condition? So this is for the when you are doing for the space, and that is for the vectors. So this problem, if you see it, so this is for when you are doing for the column space, as here it is mentioned for the column spaces. What is this?
So sir, if I have more than one vectors, I should go with this one. If I have only one
column
vector,
space, yes,
I should
right.
go for them.
Yeah, if your this is. Suppose your A is a kind of a matrix, so we can go with this one. The projection matrix in that case is going to be this one, or this is how it is. And if your the vector is,
no, so please continue.
And if your the projection is for the on the vector, so you can follow this one.
But sir, can I substitute, like use this small a formula for that matrix?
That is substitute means exactly matching. Is it
No,
your
like
second?
I have a matrix. I use the second formula, the small a formula for the matrix. Is it possible?
If you are doing for matrix, so yeah, you can go with this formula. This whatever you this one here. This one, and for this you are doing for vectors, so you go with this formula. So in this case, the projection matrix is going to be this one. If your if your space is given for this one, where is that? If it is asked that this one as this problem is there, where is that? This one, I think. think I just copied. Yeah, this one. This in this case. So here is how we'll solve. Either you can directly solve with this A transpose of AX and A transpose of B and find the solution of it. Okay, find the solution of it. But 1 minute, why is multiplying A? 1 minute.
Sir, because AX is B, sir. AX cap is B.
Okay, AX is.
And sir, without A, this doesn't make an identity. Sir. That's what the issue.
Oh,
I mean,
this B is our AX.
Yes, sir, B.
Okay. That's why okay.
Even if I solve the inverse, I just use the inverse property, so the whole thing becomes in identity.
Sir, A transpose A is a matrix when you are going to project it on space. It is not the scalar.
Ma'am, it's a 1x1 matrix.
No, I am just telling about why it is coming as inverse. That's the point we are discussing, right?
No, not for inverse. Okay, that is inverse is coming.
We are saying it can go down.
No. If you take it as the denominator, then it will be a matrix, right?
No, ma'am, it will be scaled. No? The matrix is itself 1x1 matrix.
No, don't take the. This is the formula for space. Projecting.
Right, ma'am.
This is not for projecting the vector on another vector line.
Ma'am, I understand the point, ma'am. But if I multiply vectors, for example, the norm is A for norm for vector A, for example, A transpose A, and norm is the length.
That is for single vector, right?
Right, ma'am. And
not for space, right?
Agree, ma'am. But it creates only one value, right?
How?
Ma'am, that is the formula
if you
for
matrix
norm,
if you take the multiplication of two matrices, it will give you another matrix 2 cross 2 into 2 cross 2. Right?
I'm not taking, ma'am. I'm not taking multiplication of two matrices. I'm saying A transpose into A. A is a vector. A transpose A becomes a norm, ma'am. That is the length. Length is a number, one value. Agree? This is the formula, ma'am, for the norm, the length of the vector. A transpose into A.
So if it is a vector, then it is
then you have to make it as denominator.
Ma'am, that becomes denominator. What are like reduction of the what are like in the understanding is that A transpose A matrix into this one, A transpose A is a matrix. It also produces a single value, no? That is a 1x1 matrix.
If it is a vector, then it will produce a single real number. Okay.
Sir, even in the case of matrix, it will also produce 1x1 matrix, which is a scalar, which is acting as a scalar. That the other guy is saying.
In case of matrix, it won't produce a scalar.
How it will produce?
Yes, that's what my point.
In case of matrix,
it won't produce a single value. So if you are trying to calculate,
it will produce a matrix only.
It won't produce a scalar, no?
That's why I told you 2 cross 2 into 2 cross 2. It will give you the 2 cross 2 again.
A matrix, and you are finding the inverse of it. It will be a
so it won't give you the scalar factor. It will give you the matrix.
Only in the case of 1 cross 2 and 2 cross 1.
Yes.
Else it will always give you
if it is a 1 cross 2 or 2 cross 1 means vector, then it will give the scalar in that case. If it is a matrix, then it is a matrix.
If it is a matrix, we have to use this formula. If it is a scalar, then we have to go with the denominator formula. The professor clearly explained it. If you are projecting the vector on a line, that is, then you have to go with that formula. If you are projecting a vector on a space, then you have to follow this, like this he told. If you watch this lecture, then you can get this point.
Space means if it is a mention, so space means the case is that you just
the matrix.
So space means surely in the space means you write the span, no? Span of some vector. So you will need to write as the column. You will form the columns of the matrix and then follow the formula. This formula. Yes, yes.
Right.
If you take just a two-dimensional space, it requires two vectors, right? So it will form the matrix only. It is not going to be a vector. Two vectors can form the matrix. Okay, you got it?
Okay.
Yes,
And that's all the end of this session also.
That was the difference between this and this. Okay. Got it. Thank you so much.
If you watch week 3 lecture, revised revisit vector space. In that lecture, Professor Arun Rajkumar explained it very well. Column space, row space. You just go through it and watch it at least once.
Yes, ma'am. I had watched it recently. I used so many
Yeah, he has
concepts.
explained it with the 3D image and 2D space.
Yes, ma'am.
How it is getting transformed. All these stuff he has explained it very well.
Okay.
Sir,
That's
if you
all
could
for
prepare,
yes.
please, just 2 minutes or so. Just 2 minutes.
Okay.
I mean, I would like to involve everybody. Like everybody should please contribute this. Sir, in that part that we were discussing about column, row operation on column and row operation on transpose of A, right? Prior to this concept or this concept. So, sir, I had this intuition. I had this something clicked that suppose for a row column matrix, I had first column is of rice, second column is sugar, and third column is of wheat. Okay, sir. So when I perform row operations, I subtract rice from rice, sugar from sugar, and wheat from wheat, right, sir?
Row operation. Yes.
Right, sir. Right. But if I transpose it, then it becomes the first one is like sugar or different, like sugar, wheat, rice, or that. Okay. So if I perform row operation on that, can I subtract rice from sugar or sugar from like wheat? Is it possible?
No.
In that case.
No. It will not. If you do transpose of it and then again perform the row operation, it is not going to be that.
Sir, but in the transpose operation, so the rows become that, no? First row is wheat, second row is rice, third row is sugar.
Let me make it. So let me make it. So this is let me make it. This is rice. Yes. This is dal. This is wheat.
This is A, sir. A matrix.
So and here some entries are there. Okay, so let's say 1, 2, 3, 4.
Even if
5,
the matrices
6.
are not there, it's just about the conceptual thing. I subtract. I perform row operations and rice subtracted from rice 2 times rice.
Let me make it. So yeah, without making that, it will not visible. So let me 3, 4, 5, 6, 7, 8, 9.
Right.
Okay. Right. Now, if you are doing the row operation here, so means operation you are between the rice and rice, dal and dal, and wheat and wheat. If you do the transpose of it,
so first row becomes rice. Second row becomes dal, third row becomes other.
Okay, and here it is going to be 1, 2, 3. So this is 1, 4, 5. Okay, sorry, 1, 4, 7, and this is 2, 5, 8, and this is 3, 6, 9. And now if you are performing the row operations,
is it acceptable? Valid, sir? Like, am I allowed to do that?
Okay, just a second. So now if you are doing the row operations here, so this is okay. This is done.
Dal on rice or wheat on dal.
Okay. Okay.
That was my. I couldn't remember that.
Okay. We are performing on rice and dal and okay.
Is it acceptable, right, sir? Is it?
It is acceptable. It's depend on how the problem is asked.
Yeah, sir. Actually, it will depend on the equations also, right? Or how is the problem being framed?
How the problem is asked is based on that only. That is fine. That we here when we are doing transpose and okay, so we are actually performing between the operations rice and dal wheat. But it's depend on the question what is asking. That is it asking row operations here? So this is the row operations it done. If it is asked the column operation, so if you do the column operation, so see that means the row is sorry. If If you're performing the row operation, then you are getting here the row space. And if it is asked the column operation, then column space. Because column space means you are taking the column and the span of it. So get the basis of it.
Hello.
Yeah, it is going to be a simplified. Sorry, you are audible. You are not able to listen us.
No, sir. Actually, the network there was some network issue. Yes, sir.
Okay, so here is in the when we are doing the transpose, yeah, we are doing the operations on the rice and dal, wheat in between. If we do the transpose and then do row operation. But yeah, if it is asked the question for the column space, then there is no change even, because column space, finding the column space of here or row space of here, both are same. So that's why if you are doing the transpose of it, and then basis of it is going to be just the whatever the simplified one you got.
But sir, will the basis be same if I have row echelon form for column subspace and row echelon form from the transformed subspace? Will they be same?
Basis, there is not basis. So there is one basis for a space. Otherwise, there are infinitely many bases. Which basis you are saying to be the same? The question is which basis you are saying.
Only standard.
A standard basis is going to be same.
No, for this operation, row operation on column and then row operation on transpose. If I perform row operation, will the standard basis be same for both? That's what that was my.
So it's depend on if your problem is for a square matrix, then standard basis is same for both. If your matrix is not a square, then it's depend on the question. The column space is going to be changed in that case, and row dimension of the row space is going to be changed in that case. Then the standard basis are not same, right? In that case.
I agree with your point, sir. I got your point, sir. I rephrase my question. For column space, if I perform row operation, it will produce some base, right? And for the transpose matrix, if I again apply the row operations, will it produce the same base?
Yes, it will produce the same basis. Same basis means standard order basis.
Standard. How come it produce standards? So we are in here we are dealing rice with rice, dal with dal. In the transpose, we are dealing dal with rice and some other item with dal.
So simply reason is change in the reduced row echelon form, RREF. RREF. You will always get here if it is a 2. So if here it is in the rank 2, then rank 2 will get the 2-dimensional. Here if it is a 3, then you will get the standard order basis of order 3. Means standard order basis means 3. So it's depends. Just do the RREF. It is going to be the same for both. Okay.
Sure, sir. I'll try it because I'm just not able to grasp this concept. Why are we getting the same? I mean, in my understanding, it was that for the transpose, I should go for column operations that will produce the same as the column space of having row operation. But I'll try it, sir.
Actually, it is related to the context, means in which context the question is asked. You a bit confused with the row and columns, but you didn't clearly specify, are you finding the row space or are you finding the column space? In that context, it is going to be true. Otherwise, it will never be clear to you that how it is asking, like what is the relation in that, or how these two are going to be same. Still, see, I am also a bit confused that in which context you are saying. Without clarifying that, are you talking about the row space or are you talking about the column space? It won't be clear.
I was going for the comparison, sir. Column space, standard basis for column space, and the standard basis for transform A.
So if so you can now consume it or assume it if your matrix order is not square. In that case, standard order basis or the space you are not same, how the column space and row space are going, or order basis are same. Standard order basis. Okay. Because there is. So if you are doing transpose, so what you are asking? In which purpose you are doing transpose? What is the context of doing transpose? Why you are doing transpose?
For the comparison, sir, like I had this notion in mind that for A transpose, I do something, I create a
between
basis.
which comparison between which?
That's what, sir. This the second part is regarding the transpose. There's a matrix, column matrix, column matrix. I perform the row operations. I get a standard basis, right, sir? If I compare it with the
You will
same
not
matrix,
get the standard basis. It doesn't matter how will, if you are performing the row operation, how will get the standard basis? You will get a basis. You cannot say that you are getting the standard order basis. You will get a basis. That's all. You cannot say you are getting the standard order basis. How will get? If you are performing here the row operation, you will not get the standard order basis. You will get a basis. What is the difference between basis and standard order basis?
The standard order basis is basically the minimum value.
No, that is the wrong answer.
Sir,
Standard order basis is 1 0 0 0 1 0 0 0 1.
Ah, that is what I was coming to. That is standard order basis, right?
Yes.
Right. That is standard order basis. For transpose, if I take the same matrix, I perform the row operation only. I have transposed the matrix, but I'm also only performing row operations, or row echelon form, reduced row echelon form. So basis will be affected now. Then the basis will not be same. That was my notion.
Yes, here the order is now changed. If you are transpose, this is 2 cross 3. So basis is now changed now. So basis is of what? Basis of what? The question is basis of what? If you are doing the transpose, basis of what? Of what basis you are talking? Basis of what? That is what I'm asking. Here is what basis? Here is if you are doing the row operation of the on same matrix, what basis? Of which space you are talking about the basis? Which basis?
Right.
Sorry, which space?
Apply row echelon form. I like apply echelon
Tell me the space. Tell me the space. Tell me the space. Of which basis you are talking about? If you are talking the basis, surely the space is there. No? Of what is the space here? What is the space here? So first, let me know what is the space here.
The matrix you're talking about, sir.
You are performing row operation to find what?
Matrix. Above matrix. Above 3 cross 3 matrix that we have mentioned.
Okay, so what you are finding here? If you are finding, so what you are finding here?
I'm applying row reduced echelon form and I'm finding the standard basis, sir. And
of which space? Of standard basis of which space? Standard basis of which space you are finding? That is what my question. Which space? What is that your space?
So which space? Could you please give options like what space?
Which is, see, there is no meaning of saying basis. Basis without the space, there is no meaning of basis. So which space you are finding the basis?
Basis of column space or row space. So sir is asking.
Basis of which space you are finding? Basis of row space, basis of column space, basis of some other space. Which space you are finding the basis?
Sir, what space? The row reduced echelon form produces? I believe produces the column.
No, see, row echelon form nothing produces. Just simplified the numbers. It is just simplified the numbers. It's your context that in which sense you are finding the basis. That is what we are asking. That is your confusion now.
Column space.
Column space.
Yes.
So you are finding the basis for the column space. So why you are doing row space on the same matrix? No need of it. First find the transpose of it. Okay, first find the transpose, which is this one. Now find the basis for that. Now perform there is no need of doing this one. If you are finding the basis for the column space, first do the transpose and then perform the row operation, and whatever the basis you are finding, okay, you will get that.
Right, sir. And with the first matrix, I go for the row space. Then also I'll
and now here is you are finding the row space of this matrix, means this matrix row space. So you perform now the row operation, you will find the basis.
Again row operations, sir. I do it row operation for transpose.
If you said no, you are finding the row space, basis for the row space. Yes, you got that. Okay, fine. So now you are comparing this basis to the column space basis.
Yes, sir. In my
These
notion,
two
it
are
must be
different.
transpose, right? The standard basis must be transpose of the first operation and second operation.
No, no, I can't answer now. Okay. Without the context, you cannot answer. Even I cannot answer.
Sir, we produce
Okay.
the, for example, for the first matrix, we did the column, this row, for example. I'm producing some basis, some
Which
standard basis,
basis?
right?
The question you're putting basis the row
Row, sir.
you are doing.
Row,
Okay.
row,
You are getting
row
the row.
space.
Basis for the row space. Okay.
Right,
Now
sir.
what
And
you are doing?
you said we implement the row reduced echelon form, right, sir?
Okay.
And we are finding standard basis. And then we again transpose, or for the column vector, we are also using the row reduced echelon form.
Okay.
So should
Then
it be like operation row or should it be column? That's what my question. For the transpose.
so
Because
this is
see now, the right.
these two are not same. Okay, so my answer is these two are not same. You did for
And then the
basis, you
transpose form.
find the basis for the column space. Here you find the basis for the row space, and both spaces are different. So bases are different. Even the standard ordered basis is also different. Okay.
But sir, they were the transpose, right? So row becomes column, column becomes row.
So no. So just assume. Okay. So my answer is no. Both are not same. Now take your example. Take some example of 3x2 matrix. Do that and find the answer. Compare the answer. Now your work is there. Try to do with the example. Without doing practice or without doing some examples, you cannot argue. You have to do some calculation first. You cannot even argue that how this could be, how this could be. So without pen and paper, you cannot argue. Okay.
Right. So could you share the above M matrix, sir? I'll just try on that one. The 3x3 matrix.
Now I will give to you. Now I will give to you. Try yourself. Because if you will discuss, then I will not end up with, because your diet is. I am very surprised with this. How much you confuse with the row and column. How you are doing the row operation and getting the basis without saying the context of which space you are talking.
Right, sir. On your guidance, sir, I'll definitely try this one, and I'll
Yes.
find the spaces and
Just do the pen and paper, and you will get clarified. You are not doing pen and paper. You're just arguing with me, means discussing with me, but you are not doing on pen paper how it's happening. Just do on pen paper one by one step. Whatever you are doing, no, just do one by one steps, and either if you have, you can post in discourse. Okay, tagging to me with the pictures. We'll discuss there also, so that I will get that. Okay, which you are. What you are comparing, which basis you are comparing, column basis, row basis, which space you are talking about.
Right.
First we have to do your own, then I will get.
Right.
Okay.
Sir.
Yes.
Thank you so much.
Sir, I have a small doubt. In week 0, statistics questions are also given, right, sir?
Okay. Yes, here it is.
Yeah, like will questions from statistics come in the quiz 1, sir? Is it there in the syllabus or not?
No. This is for just no.
Okay, only week 1 to week 5, right, sir?
Week 1 to week 5.
Yes, sir. Thank you, sir.
Any other doubt, anyone?
Sir, please, in the next session, sir, please take a question or take a problem related to the triangularization of Hermitian matrix, unitary matrix. Sorry.
Yes.
In the next session, yeah. Because even some amount of Gram-Smith is also involved, right? So in case, just take a problem, sir, that day. One problem will do.
Okay, yes, missed that. Okay. Even I said, to post.
Saturday, sir.
Yeah, we are good. Yeah. Yes. Okay. Okay. Thanks, everyone. Thanks for joining.
Thank you.
Okay.
Thank you so much for
Good
time.
night.
Good night.
Okay. Good night. Good night.